Okay, welcome everybody to our Sierra Applied Math seminar. We have the great pleasure to have Dr. David Rolnick as our guest speaker today. David is an assistant professor of computer science at McGill. He's also a MEDA core member since 2020. He got his PhD in applied mathematics from MIT in 2018. Then he held an NSF postdoctoral fellowship from 2018 to 2020. Then he came here in Montreal. He has been a Canada CIFAR AI chair since 2021, and also remarkably got a prestigious award. He was listed as in the list of MIT Technology Review 35 innovators under 35 in 2021. So our great pleasure to have him speaking for us today, and take it away.
Thank you so much. It's a pleasure to be here. Please feel free to drop questions in the chat while I'm going if you don't understand something, or if there's an interesting direction that we can go in. This can be flexible. We can take this in different levels of depth and different things depending on what people seem to be interested in. So as introduced, I'm a mathematician who's turned to deep learning. I guess Erdős would say that I've died. I've left pure math. I used to be a discrete mathematician. And a lot of what my group does is look at the theoretical foundations of deep learning, why deep neural networks work so well, because we're building, computer scientists are building this field of deep learning, and it's sort of built on sand. There aren't clear theoretical foundations for a lot of the field. What is deep learning? It's loosely inspired by biological neural networks in the brain. I'm not going to give that much of an introduction here because I know that many people in the audience are well aware of deep learning, or yourselves doing research in it. Artificial neural networks are a way to represent functions. You can represent a complicated function essentially as a composition of simple functions, where the simple functions are composed according to a network structure. The idea basically is that well, I'll get into an example in a moment, but the network structure refers to the way in which nonlinear functions are composed according to linear transformations. The goal of deep learning is typically to learn from data to approximate a real-world function with the neural network family of functions. And importantly, different network structures, which are also called architectures, make it easier to express and learn certain functions. And that's what we're going to be focusing on here. With the emphasis being on really understanding the relationship between the structure of a neural network and the functions that get expressed by that network. Now, here is an example of maybe the most basic kind of neural network, which will be roughly what we're looking at, though the results will generalize a bit more broadly than that. And here we have this graphical structure. You should read it from left to right. People sometimes do it top down or bottom up, but here we'll do it from left to right. This is a layered graph. So there's one layer here, another layer here, another layer here, and so on. You could imagine many different layers. And in each layer of the graph, the vertices are connected to the vertices in the preceding layer and in the subsequent layer. The depth is the number of layers between the input and the output, and the width is the size of the layer. So here we have two hidden layers, layer 1 and layer 2, each of width 5. How does this relate to an actual function? Well, we can write down a function which is represented by this graph according to parameters which exist on the vertices and edges of the graph. So the vertices are associated with entries in these vectors B. These are called biases. So there's an entry for every one of these hidden layers for one of these bias vectors. And for all the edges, there are associated coefficients in weight matrices. And so the overall function computed by the network depends upon the variables associated with the vertices and with the edges. You can think of it as alternating linear and nonlinear transformations. If you take an input vector x, which is represented with each of the coordinates of the input vector being one of these vertices, you multiply it by the weight matrix. So you send the signal along all of these edges, you do a linear transformation, and you add the biases, so it becomes an affine transformation, and that gives you the values at these vertices. So you take in this vector, you get this vector out. So it starts at, in this case, dimension 2, then becomes dimension 5. Then you take a nonlinear function, sigma, and you apply it at each one of these vertices. So you are applying it component-wise to this vector. And then you repeat. You are alternating between these affine transformations, multiplying by a weight matrix, adding a constant vector, and applying this nonlinear function, which is often, and in the case of this lecture, going to be the activation function ReLU, which is just the max of 0 and z. There are a bunch of different ways that one can interpret this. There's a lot of great work starting to think of this from a tropical geometry perspective, which I am not going to get into at all. But there are a lot of different ways that one might be interested in this mathematically, and we will get into one of the ways that one can do that. So, but again, think of this as an alternating composition of linear and nonlinear functions, or affine and nonlinear functions, giving you an output. Okay, so as I've suggested, the field of deep learning is built on linear algebra, but it's a little bit fuzzy about exactly how that linear algebra is giving you the answers that you want. This is basically the process in machine learning. You just sort of stir the linear algebra until it gives you the answers that you want. Among the ways in which this takes place is deep learning architectures, the structure of the graph, which we looked at fully connected networks, but there are much more complicated architectures with more different things connected to different things and different kinds of operations which are being included within the neural network. And these architectures are often chosen with some degree of trial and error. One may ask, how are the functions computed by a network influenced by its architecture? The architecture, again, being the structure of the network or the graph. So how does changing the graph change the functions? And what theoretical frameworks are needed to analyze this? So one of the things that was observed early on in deep learning, in fact, gave rise to a lot of the interest in deep learning, was that it seems like greater depth makes it easier to express certain functions. Where you concatenate more, you compose more functions, you have more layers in your neural network, you can express more complicated functions. So there are various results that one can think about here. So universal approximation theorems, of which there are several different variants, say that even if you have a depth 1 neural network, if you have unbounded width, so as many neurons as you want, you could approximate any function under certain natural assumptions. Now, the important thing is unbounded width. So, for example, if you're working with a ReLU network, you might imagine, well, obviously you can approximate any function with a piecewise linear function. Using a single hidden layer of ReLUs, you can actually get any piecewise linear function. So this is not that surprising. One can ask whether just what the unbounded width assumption is concealing, and various work, including some that I've worked on myself, it looks at different measures of complexity for functions and basically says if you have only depth 1, you require exponentially more neurons than if you had greater depth in order to express certain complicated functions. So, for example, if you are looking at certain topological invariants and you want to design a function that is very complex with respect to these topological invariants, that's the results of Bianchini and Scarzelli, then you can do it with many fewer total neurons. I'm sorry, I realize I'm using the word neuron. That just means nodes, vertices in the graph. Is by analogy to the biological neural network case. A neuron is just one of these things. So each of these are neurons, 5 neurons here. So the number of vertices, neurons in your network, or the number of edges, so the number of weights, are natural measures of size, and you can show that you need exponentially many more neurons, or exponentially many more weights, or more generally exponentially many more parameters in order to express certain functions. If you're allowed only one hidden layer, then if you can go deeper. This is the case with respect to topological invariance. It's the case with respect to curvature, path length, number of pieces in a piecewise linear function, which we'll be getting into in a moment. You can express more complicated functions more succinctly using deeper networks. However, that is not necessarily the end of the picture. This seems to say deeper networks are able to express more complicated functions, but are networks actually using their full expressivity in practice? And some reasons why one might think that this is not necessarily the case. Better architectures don't actually convey more expressivity. The goal of neural network of deep learning is, in many cases, to come up with architectures that are well suited to particular function classes. So, for example, if you're working with computer vision, you might be looking at function approximators that are well suited to working with image data. And better architectures for a given task do not necessarily give you more expressivity. That's not necessarily the reason why they're good. In convolutional neural networks, which are used typically in image processing, they have what's called weight sharing, which is basically saying that you're performing the same operation across different parts of the image, which is really good if you are trying to convey an inductive bias that something that's in one part of the image is sort of the same as if it's in another part of the image. But it actually reduces expressivity since you are sharing the weights between different parts of the network. Likewise, if you are familiar with residual networks or ResNets, they have these things called skip connections, which are skipping from one layer down to layers, several depths lower in the network. So it is changing our picture a little bit. You have edges skipping between many layers, but this actually keeps the expressivity the same. It's not changing the set of functions that can be expressed by the network. It is doing something else. And what it has been observed is that it's changing the functions that the network is likely to learn in practice. So these are ultimately changing the inductive biases of the network. They're not changing the set of functions that can be expressed. And then another motivation for us thinking about networks not necessarily using their full expressivity, and the full expressivity not being the most important thing, is distillation, where you can train a shallow neural network to imitate a deep neural network. And in this case, you have the situation is that you have trained a deep neural network. I haven't really gotten into training, but this is a process that basically involves the chain rule and what's called backpropagation, where you change the parameters of the neural network, those weight matrices and bias vectors, in order to express a given function. You can train a deep network to fit data, and then you can train a shallow network, a network with fewer layers, to imitate the results of the deep network and have it represent very much the same function. So the idea being that once a deep network has been able to express a certain function, you can train a shallow network that very well approximates the deep network. Even though more layers, a deeper network is supposed to be able to represent more complicated functions, in practice, we're seeing that shallow networks can often represent the same functions approximately as deep networks. Here's that's some context on why maybe expressivity isn't the full picture. And so what we're now going to look at is looking at the functions computed by a neural network, at fixing the architecture and letting the weights and biases vary. That means fix the structure of the dimensions of all the inner vectors, what is connected to what, and you're letting the parameters of the weight matrices and bias vectors vary. You're seeing what functions can be expressed, and you're going to look at the set of functions that the network can express, which is this big set. We're also going to look at the set of functions that the network can learn in practice, which is within that big set. A set of functions that the network is in some sense likely to learn. This is a fuzzy set. It's not exact. It's not fully defined. You can think of this as the subset of the set of functions that the network can express, which has appreciable measure, the subset with appreciable measure given to it. And then within this, there is the set of functions that the network expresses at initialization. So typically the way that deep learning works is you randomly set the weights and then you perturb the weights according to gradient descent and the chain rule in order to fit a certain function. So we're going to look at the set of functions computed with non-vanishing probability by networks at initialization. Are there any questions about anything that I have said so far? As people are coming in from lots of different backgrounds, I apologize for those who are deep learning researchers for this slow introduction to deep learning, and apologize for those who haven't seen deep learning before for it not being slow enough.
I have a question. I think it's more of a historical question.
Yes.
In the sense that the ReLU function, if you see this whole business for the first time, it seems kind of arbitrary. And is it an experimental thing that people started using it and it turned out to work well? Or, I mean, was the theory there beforehand?
There are various options that you might be interested in for what's called an activation function, your nonlinear function. The only thing you really want is for it to be nonlinear. Though surprisingly, if you make it be linear, you do get interesting inductive biases. It's not the same thing having a deep linear network as having a shallow linear network. The way that the gradient descent works means that you actually have biases towards different kinds of functions. There's a regularization. People look at the matrix norms that get induced as inductive biases. It's like regularizing with a matrix norm if you fit a linear function using a deep linear network. But anyway, the neuroscience motivation might be to do something like a sigmoid function that looks like this. I'm not sure whichever way I am around on your screen.
Oh.
So a sigmoid function would be what the neuroscientists might do. But this is not as good in practice in deep learning for two reasons. Feel other people can weigh in with more reasons, but one of the reasons is that if you're far out along the sigmoids, the gradients become zero. So it's very hard to learn unless you're in the critical zone where the gradient is a reasonable size. So the good thing about the ReLU is that for half the domain, the gradient is non-zero and very far away from zero. So you have an appreciable learning signal. And that means that for about half the neurons, the gradient is appreciable. And so for any particular data point, or as you go over lots of data points, every neuron will end up getting a gradient. Whereas if you were with a sigmoid, it would be quite possible that a large fraction of your network would just have zero gradient because the scale of those neurons would be such that it was always very far out on one of the tails of the sigmoid. So that's one reason. The other reason is that it's actually just way easier to compute.
Okay, thanks.
The max operation and the identity are both very easy, not surprisingly.
Yeah, I mean, it's the simplest way to get piecewise linear functions, I would say. Yeah.
Exactly.
It's piecewise affine functions in this case. Yeah.
Indeed. More questions? Great. So we're now going to take advantage of the fact, thank you for that segue, that this gives you a piecewise linear function, piecewise affine. So the ReLU is piecewise linear. And we're going to look at this particular measure of expressivity of complex functions in a neural network, which is the number of pieces. So you can think of this network as defining a piecewise linear function, since it relies on this piecewise linear activation function from inputs to outputs. Remember again that a neural network is alternating between affine transformations and applications of, in this case, the ReLU, which, since it is piecewise linear, the whole thing is piecewise linear. So this is what a ReLU network function might look like. This is here taking two input dimensions and giving you one output dimension. And it is, you have all these pieces, and you can think of them in lots of different ways. These are the pieces on which the gradient of the network is constant. For example, gradient of the output with respect to the input. Okay, so this is a very natural measure of, this gives you a very natural measure of complexity of the function, because if you have more pieces, you can intuitively approximate a more complicated function. If you're trying to approximate this curvy function, you want more pieces to do it with. So you can ask, how many regions are there? This is, again, the formula for the neural network. So how many regions are there? This is, again, these are regions of input space on which the function is linear. How many linear regions are there for such a function? Bearing in mind that each region you can think of as a pattern of off and on ReLUs. Because if you set the ReLUs to be 0 or 7, if you get rid of the pieces, then that gives you a particular linear function. What is the minimum number of regions that you could have? Anyone in the chat or unmuting? 1, great. It could just be the constant function. What about the maximum number? Bearing in mind that each region corresponds to a pattern of off and on ReLUs, either 0 or z. It's going to be more than log depth. So given a pattern of off and on ReLUs, well, given a region, there is a pattern of off and on ReLUs that defines that region. It's not necessarily true that every pattern of off and on ReLUs gives you a region. Some of them might not be, you might not end up having an input that gives you that pattern of offs and ons. But if there is an input that gives you that, then that'll give you, then there is a region.
The number of nodes?
Well, but each node has 2 possibilities, off or on. You have you have n nodes, n ReLUs, so n things that could be off or on. Each of them can be off or on. You have 2 possibilities. So the naive band is 2 to the number of neurons. It's a naive band. Doesn't mean you can attain this band. But turns out you actually can. Almost. You can put a constant here. If you have a deep, skinny network, you can have 2 to the number of neurons times a constant. And the way that this works is you can end up getting the sawtooth function. You can also think of this like XOR, where you are like a parity function, where you have exponentially many teeth in the sawtooth function in the depth of the network. Every time you add a layer of the network, and the layer could just be like 2 neurons, you double the number of teeth in the sawtooth function. Okay, I won't go into that construction, but this is a way that you can construct a network that does this. Is this typical behavior? Do you have any thoughts on that? Is the number of regions normally like 2 to the number of neurons? Is that normally what it is? I know I was coming from Ramsey theory and other areas where I was expecting random graphs to be very similar to the upper bounds. One might expect that a random neural network would be similar to the upper bound, since the upper bound is attainable. Turns out this is not the case. The number of regions is very far from the upper bound, typically. So here is how it can be formulated. Suppose you have a network with piecewise linear activation. For example, ReLU, it will hold for any other piecewise linear activation function, with weights and biases drawn from some distribution. This distribution could be at initialization of the network. It could be after training the network on some data. Then, for any curve through your input space, the number of regions that intersect this curve, it could be exponential in the number of neurons in the network, but is actually linear in the number of neurons. This is expectation over the distribution on the weights and biases. Fix your architecture, draw your weights and biases. Random network of that structure has only linearly many regions intersecting a given curve. It also depends on the length of the curve, obviously. Now, what are the assumptions? Are there any assumptions? Well, there's basically only one assumption. There's some other technical assumptions, but assuming that the gradient at every neuron in the network is bounded in norm. And that's expectation, again, over the distribution of weights and biases. So if you have a neuron in the network, you can think of this as an entry of one of the intermediate vectors, and you're doing this, these successive affine transformations and hitting it with nonlinear functions. If this gradient is bounded for every neuron, network, then the number of regions is going to be much, much lower than the upper bound in expectation. And this condition provably holds for networks at initialization. There's a standard initialization that is used for neural networks. It's called he-normal. And this, I can go into the motivation behind that, but there's a standard initialization. If you do this, then provably this condition will hold, but it should also actually hold for neural networks that have been trained on data, that have learned to approximate natural functions. Why is that the case? Because the way that neural networks are typically trained is using gradient descent. And if you're going to have a gradient-based algorithm, then gradients need to be well controlled. If this gradient were to start exploding, if it were not bounded, then your gradient descent would fail. So again, this is showing that the expected number of regions could be exponential, but it's actually linear. If you're looking at regions intersecting a curve, I'll look at generalizations in a moment. This shows that the expected number of regions is actually independent of the depth of the neural network. And that's a big thing. So we thought the deeper networks were more expressive, and they are if you look at the upper bound, but they're not more expressive if you look at the expected value. What it's showing is that the number of neurons is the only thing dictating the expected number of regions, even though the maximum number of regions could be exponential in depth. This holds for fully connected, also holds for convolutional layers and skip connections if you're interested in that sort of thing. Questions about this? It's hard, since I don't see people's videos, to tell whether everybody is bored by this or not understanding.
No, David, I have a question about this
Yes.
theorem. So is there any assumption on the smoothness of the curve? Like, can you have pathologic things like space filling curves?
Yeah, no, like there are nice assumptions on that. However, a space filling curve wouldn't work very well because the length is
right. The length would be, yeah. Okay, so there are some assumptions.
Yes, there are some assumptions. It's not completely assumption free.
Okay.
But this is the only for a computer scientist. This is the only assumption. For a mathematician, there are a bunch of other assumptions to say so that it actually like holds mathematically. The distribution of the biases has to be nice, for example.
Right.
Here's an intuition for why this is true. Suppose you're going to look at you're going to this is going to be like the linearity of expectation intuition for why this is working. You travel along your line or your curve L, okay, and you're going to see when you intersect a new region. Moving along my curve, transition when a particular ReLU in the network switches from off to on. That's the only thing that can lead you to transition from one region to another. And with probability 1, only one ReLU is transitioning at that point. So there's exactly one neuron which is switching from off to on. That gives you a new region, new linear function now. So that occurs when some neuron in the network is 0, right? You have this ReLU. The ReLU is this max of 0 and z. So it switches from one piece to the other piece at 0. Or you're shifted by bias, shifted to some bias. But there is this point. You're saying z of x for some z equals 0 when you're transitioning between regions. Now, how often is that going to occur? Many solutions are unlikely unless the gradient is very, very big. You're not going to have many solutions to this unless you're a strongly oscillatory function. And so you're going to, in the end, expect O of 1 solutions for every neuron in the network to this equation. And so if you sum that over all of the neurons in the network, you get O of number of neurons transitions overall. This is the linearity of expectation intuition for this. There's obviously like more detail that's necessary to make this rigorous. Now, one can ask whether this is actually true in practice post initialization. So here you can see these are training curves. So this is a neural network that's been given some data, and over the course of the x-axis, it's seeing more and more data. That's what is meant by epoch. So it's seeing more and more data, and it's learning to fit this data. And this your product is seeing on the y-axis the number of regions divided by the number of neurons, because we're expecting the number of regions along a curve to be linear in the number of neurons. So we're normalizing by the number of neurons. Each of these curves is a different network. So it's different architectures of network. And you can see that the number of regions starts out at the number of neurons, and then it goes down in this case. If you zoom out, it'll actually go down, and then it'll go up a bit, but it's not going to go up very much. So basically, even during training, the number of regions is going to stay tightly controlled. It's not going to go blowing up to infinity. So what we're seeing is, in practice, for networks that are actually being trained to do a simple task, this is MNIST, one of the standard machine learning tasks, the number of regions is not low. Now, for someone who knows MNIST and the deep learning context for it, you can cry foul for this figure, because MNIST is a very simple task. And you might reasonably say that the networks don't need a large number of regions in order to learn MNIST. So there's no reason for them to learn a more complicated function. So here is a different plot. This is zooming out a bit. And you can see here the red curve is just the same thing that we were seeing before. This is MNIST. And then the purple curve up here is MNIST with random labels. It's trying to learn a completely random function. It's given some data, and that has no structure to it. It's just given random labels. This is a function which the neural network will need as many regions as possible to fit. In fact, it's not able to fit it with this size of architecture. It's not possible for the neural network to fit it unless it had more parameters. But even though it's trying to fit this pathological function, which has just completely random labels, it would benefit from more linear regions, but it's still not able to get more linear regions than basically at initialization. So it starts out with 96 regions along a line. The expected number is depth 3, width 32, so you expect linear in 96 neurons, and actually the constant, I won't go into it, the constant should be 1, so you expect 96 regions at initialization. You get 96 regions at initialization and expectation, and it never goes very far above 96, even during training. Okay. So what we're seeing, again, to interpret this, is neural networks are capable of expressing exponentially many regions, but you're never going to see that in practice, even when it would be useful for them to do that. Some generalizations, you might wonder, we were looking at number of regions intersecting a line. That's a bit weird. What about number of regions intersecting a higher dimensional subset of input space, or all of input space? So if you have some n-dimensional subset of input space, the number of regions intersecting the subset is going to be number of neurons, or bounded by the number of neurons raised to the nth power. Which intuitively is actually the smallest that you might imagine for this. If you think about like number of regions, if you have like n hyperplane, sorry, a number of neurons hyperplanes in n-dimensional space, like this is actually as small a number of regions as you might imagine getting. We'll get into visualizations for this kind of thing in a moment. So hold your horses on that. Another generalization is you can look at the expected distance to the nearest region boundary. And one can have access to this. We actually have like expected values on lots of different stats of like all the different codimension, like all the different dimensional stats of this like dissection into linear regions. You can look at the surface area of the boundary. You can look at different codimension volumes of the boundary. But if you look at the expected distance from x to the nearest region boundary, you get that it's actually quite large. You could imagine this being 1 over exponential in the number of neurons, because the number of regions could be exponential in the number of neurons, but you get that instead of being 1 over exponential in the number of neurons, it's just the reciprocal of the number of neurons. This matters, that the distance from x from any point to the nearest region boundary is an expectation big. That means that there's a little region around any data point where the function is linear. there's a pretty big ball around any data point where the function is linear. That means, if for those who are familiar with deep learning, that there's a limit to how much of an adversarial perturbation you could have on a data point. Because adversarial perturbations are these things where you move around data points so that they cross over into different decision regions of a neural network, and the neural network behaves very differently on them. But if you're in the same linear region, then the neural network can't be pathological because it's just a linear function. Okay. Are there questions on this? Again, I'm not sure if people are bored or confused or playing Wordle. Okay. So here I'll skip over this, but this is just showing the distance to the nearest region boundary as you train the neural network. There is some cool math going on here in that the distance starts out pretty large. It actually goes up and then it goes back down. It stays pretty large, but we don't understand why it goes up like this. It's quite interesting. It goes up at a certain test accuracy, just regardless of the architecture of the neural network. We don't understand why this thing happens, but it is perfectly predicted by our theorem that the distance is always very, very large. It's all that our theorem is actually saying. Never goes below a certain amount. Okay. Now we're going to transition to something else. And this is going to start looking like hyperplane arrangements. Because this is secretly what's going on under the hood with all these linear regions. So let's take a look. This is a picture of linear regions. This is if you took that, remember we had this plot of linear regions of a neural network. Neural networks, you know, this class of functions, and you can divide them up into these linear regions. And here is if you were looking from above on that graph. These are all the linear regions for a function that is taking 2 input dimensions. Okay, so this is one input dimension. This is another input dimension. And as you go over this input space, these are the linear regions into which the neural network is decomposed. Like over this region, the neural network has a single linear function. Over this one, it's another linear function, and so on. And this is pretty and colorful. But some real structure comes out if you highlight the boundaries. So now you can really start to see some stuff going on. So one of the things you can start to see is there are these nice lines. And then if you take out the lines, there are some other things which are like these bendy lines. Like this line goes around here. And this line goes around here and it bends, and you can follow these lines. It's like spaghetti. You'll find some of these are straight lines and some of these are bendy lines. And this is a generalization of a hyperplane arrangement where some of the hyperplanes are bending, and the hyperplanes are bending when they intersect other hyperplanes. So get into why this is the case. So motivation for the more applied people, why we are interested in this is we're going to solve a long-standing problem of can the structure and weights of a neural network be recovered from the function that it computes. And this it's unclear. It was unclear whether you could even solve this. And it's useful because many neural networks are actually kept confidential. They're proprietary. They have public output, and private structure and weights. And if you could know what the network is just by querying it, by observing the functions, by giving it an input and observing its output, then you could maybe recover the network. Then you could maybe recover data that was used to train the network, which might be proprietary or confidential. You might be able to design adversarial attacks where the network fails catastrophically. So it's really important to know if you can do this. It's also relevant for neuroscience because there are neural networks of a different kind, but in some respects similar in the brain. And it has actually been attempted in neuroscience. So can you reconstruct the structure and the weights of a neural network from the function that it computes, given the ability to give it an input and observe its output? So one of the preliminary questions that you might ask is it even possible to fully reverse engineer a network? Could 2 different networks define the same function? Is there ambiguity? What do people think? Can 2 different neural networks define the same function? And what are the transformations that can, if so, what can you do to a neural network to get another equivalent neural network? couple of things you might do. One sort of obvious one is permuting the neurons within any layer. The order doesn't matter. Slightly more subtle is for a ReLU network, you can scale any neuron by non-negative weight. So you can scale all the incoming weights and the bias of the network by a non-negative constant, sorry, a positive constant. And you can scale the outgoing weights by 1 over that constant. And this is the case. This is the case because the ReLU function is equivariant under multiplication by a non-negative constant, by a positive constant. Okay. So if you do this to any ReLU network, you get the same function. So you definitely can't recover the function except up to these transformations. So can you recover the structure and the weights up to permutation and scaling? That's what you might ask. Turns out the answer is yes, using linear regions in many cases. So here's a theorem. Suppose you have a fully connected ReLU network of any depth. For a neuron z in the network, we're going to let bz be the set of input points where z equals 0. We'll visualize what this is in a moment, the boundary set. Suppose that bz is a connected set and that these sets intersect for every pair of adjacent neurons, where adjacent just means like they're connected in the network. They have a weight between them, adjacent in the graph theory sense. Suppose that every boundary set is connected and that any 2 boundary sets intersect if the neurons are connected. Then, first thing, if you have the boundaries between the linear regions, it will turn out these are the boundaries between the linear regions. So if you have a set of linear region boundaries, it is possible to recover the complete structure and weights of the neural network up to permutation and scaling, except for a measure 0 set of networks. Second, it is possible to approximate the set of linear region boundaries and therefore the architecture and weights by querying the network. So by giving it an input and observing its output. So let's see why. This is the intuition. And this is also what I was actually meaning by these generalized hyperplane arrangements. So think about a neural network like this. Each of these is, well, first of all, this is a neural network, and this is the boundaries between the linear regions. And we'll see these are like a ton of structure. This is the boundaries between the linear regions for this network. It takes 2 input dimensions, gives you 1 output dimension. So we're plotting the partition of input space, this 2-dimensional input space, into linear regions defined by the pieces of the linear pieces of this function, or the affine pieces of this function. So what is this function? Each of the blue neurons is going to be 0 on when a certain affine combination of the inputs is 0, right? Because that's what these functions are. They're each affine functions of the inputs. Now, what are those functions? Well, those are just lines through 2-dimensional space. And so these gives us these lines. This is where these neurons are 0. That's where they transition from one part of their ReLU to the other part of the ReLU. What about the red neurons? The red neurons transition from one part of the ReLU to the other part of the ReLU when they are 0. But when is this neuron 0? Well, it's 0 when a certain affine combination of its inputs is 0. And its inputs are piecewise linear. So in this case, we have, this neuron is going to become 0 when a certain affine function of its inputs is 0, but that function is going to change when the blue neurons change. So what you see is this is the boundary set, the set where this one of these red neurons is 0. It's going to be a linear function until it crosses over one of these blue lines. When it crosses over one's blue lines, one of these neurons has flipped from off ReLU to on ReLU, or vice versa, and so the linear function for the red neuron changes. Same thing when it hits the next blue line, again, changes the linear function. Every time it hits one of these blue lines, it bends. So we have a boundary component where each neuron in the network equals 0 to sum up. And each one is piecewise linear. It's a bent hyperplane. In the first layer, everything's just a hyperplane because they're just affine combinations of the inputs. But for later layers, the hyperplane, the bent hyperplane, bends every time it intersects a hyperplane from one of the earlier ones. This gives you a beautiful combinatorial object. So just the first layer is a hyperplane arrangement, but then you get into these bent hyperplane arrangements. So this is the intuition behind why you can recover the function, the structure and the weights of the network from the boundaries. First of all, you can read off the first layer weights just because these blue lines, what's the equation of one of these lines? It's literally the weights going into that neuron. The equation of the blue line is the weights going into the neuron up to scaling and up to permutation because you don't know which one of the lines corresponds to which one of the neurons. And then for these other ones, it turns out that the bend here gives you the weight between the red neuron and the corresponding blue neuron. So that's why we need that the red boundary has to intersect all the blue boundaries, because if you see its intersection, the red line intersects the blue line, that gives you the weight between them. Okay, so how do you actually go about turning this into an algorithm for recovering the network? Well, you can approximate the boundary by taking a random line through input space and seeing where it transitions between different linear regions. You can find these points where it transitions between different linear regions, just empirically, doing binary search, for example, to work them out very, very effectively. And then once you got each of these points, you can work out the local, the equation of the line right around it, because these are all piecewise linear. So you can work out the equation of this line, it's a red line, work out the equation of this blue line. And this first thing you need to do is identify the first layer of the network. Identifying the first layer of the network, you extend all of these lines, or more generally hyperplanes, and you see, going off far into the distance, whether these points are still on the boundary between different linear regions. You infer the hyperplane, and you extend it out very far, and if it still is a boundary between linear regions, then this is a full hyperplane. It doesn't bend. You're good. Otherwise, it's a bent hyperplane. This red one bends. So if you extend it very far, you're no longer on the hyperplane. So you realize, oh, this one must have bent. It must be in a later layer of the network. The ones that don't bend are the first layer of the network. So by testing the hyperplanes, you can work out what's in the first layer. Then for the next layers of the network, you're going to explore these boundary intersections. Once you've worked out layer one, you know that layer two is the ones that only bend when they intersect layer one. Layer three is the ones that only bend when they intersect layer one or layer two, and so on. You can go layer-wise through the network. There's some linear algebra involved in actually working out these, but you then end up working out all the weights up to permutation, and scaling is because of the same intuition that these weights are only defined up to scaling. So there are some caveats that I can, or other considerations I can get into if we have time, but just very fast. It isn't possible to just train a neural network to recover another neural network. That really doesn't work. A lot of computer scientists suggest doing that. That really, really doesn't work. You can't find a function by gradient descent on its output. Very quickly through the assumptions, the boundary components being connected, that generally holds unless the input dimension is small. And the adjacent neurons having intersecting boundary components. This is very interesting, and we're working on this, but failure can evolve. Sometimes this fails, this assumption fails, but that can actually be because there are other isomorphisms in the network beyond permutation and scale. So it can be from unavoidable ambiguities in the network. If it does fail, then you can work out most of the network, but not the entire network. There are some plots for those who want to see that we can actually recover these weights of a neural network with unknown structure and unknown weights. We can recover them. There's a log plot up to basically perfect accuracy. I think we are at time, so I'll stop here for questions. Thank you very much for listening, and happy to dive into any part of this that people are interested in.
Thank you very much for the amazing talk. So yeah, we do have time for questions. So I invite anyone in the audience who might have any to raise their hand.
Caleb says that makes, I'm hopeful that was going to be making sense. It could be that makes no sense.
That makes, right.
Oh, sorry. I actually said that makes a lot of sense. So.
Okay, great.
Thank you.
So, okay, maybe I can break the ice with a question.
Yeah.
So, okay, you've been quantifying somehow the complexity of the functions that a network can represent by counting the number of regions.
Yeah.
I was wondering if there's some more refined measure of the complexity of this banded hyperplane arrangement that one could study. Let's say the ratio between the areas of the 2D case, the triangles you generate, or stuff like that.
Yes, great. So there are a bunch of different generalizations one could look at, or other measures, related measures. One could look at the curvature, so like how things are curving. We're currently doing that. You could look at the distortion, so how lengths and volumes get distorted. You take a certain input, and you see how it gets distorted by the function. Expected distortion of lengths and volumes. We just put out a paper on that, and it turns out that one is also tightly controlled. It had previously been assumed, a bunch of authors had stated that it grows exponentially with depth. Turns out that it doesn't. It actually stays basically the same with depth. It actually gets slightly less with depth in expectation. So again, something that could explode, the upper bound, it explodes, but with very high probability, it is tightly controlled. It doesn't actually grow with depth.
I see. Okay, so
difference between worst case and average case.
Yeah.
All of this is difference between worst case and average case.
I have a bunch of other questions, but I also want to give the opportunity to anyone who wants to ask. Please do not be shy.
David?
Yeah.
In the complexity, you have a constant C. What does it depend on?
What is the constant C? Great question.
Yeah.
So in most of these cases, C is actually not, we know what the constant C is. They're not very big. So for example, here it's like 1 over the dimension factorial. There is another part of this that depends upon like the bias distribution. But these constants boil. So in the general case, if you're working with a general distribution, it'll depend upon the distribution of weights and biases. But for the He normal distribution, these are going to be very simple constants. But it does depend on the distribution of it depends on the distribution of weights and biases. And then here it'll also depend upon the dimension a bit, but it just gets better with the dimension. Like it's 1 over n factorial, so it's actually less than 1 in that case.
Okay, thank you.
And okay, I have another question about the the kind of characterizing the type of function spaces that here we are trying to study through this counting of linear regions. So is there any link with more classical type of function spaces, or that the network is maybe tending towards approximating? I don't know. It's kind of a a broad question, but like I was wondering if there's any link, because this measure of counting the regions, I guess, might be okay. You were mentioning that there are more refined way to measure complexity, but in a way it could mislead us sometimes. Like we maybe have many regions, but at the end of the day, the arrangement is really structured, and then at the end of the day, is not as the expressivity is not as high as we might think.
Yeah, well, I mean, in some sense, we're seeing that we have fewer regions than we were expecting. We could have had exponentially many. So this is the goal is to show that there are many fewer than there could be. Even something that grows with the input dimension is very different from something that grows with the number of neurons or with the depth of the network. This is as small as it could be. This is way smaller than like exponential in the number of neurons. So yes, there are other measures of complexity. Again, I forgot, we also did surface area and other kinds of like volumes of these boundaries of linear regions. So yes, by several of these measures, they're they're unexpectedly simple. The average case scenario is much simpler than the worst case scenario. But there are definitely complexity measures that we haven't considered. Also, it is worth noting that these only work for piecewise linear networks, but there are natural analogs that are just harder to analyze for non-piecewise linear networks.
Okay, so you can extend this beyond ReLU.
We haven't proven it, but you could imagine extending it to things like boundaries between linear regions become fuzzier, right? They're places where there is a certain amount of curvature, right? You could look at integrating the curvature of the function and get bounds on that.
I had the last question if no one has any questions. Okay, so in the reverse engineering part, the final part, so did you look into the question of trying to reverse engineer a network from a limited budget of samples, like let's say assuming you cannot sample the network as much as you want?
Yes. So this was done. So we actually don't need that many samples, but if you're really budget constrained, then you could get approval guarantees with this paper by Carlini et al. So they jump off of our algorithm and do it in a different way to make it have provably low sample complexity. The trade-off there, though, is that it requires exponentially long, potentially. So low sample complexity, but it can take much longer than our algorithm.
Might have a quick question.
Yes.
So towards the end where you talk about the reverse engineering algorithm, we're only talking about like fully connected networks and feed forward. Like there's no sort of reverse loops. But in practice, I don't know much about deep learning, but I can imagine that these networks probably get pretty complicated. So I wonder like how relevant the algorithm is.
Yeah, so a lot of networks in practice are feed forward. They're generally not MLPs. So fully connected networks. We're working on ways to deal with weight sharing. Theoretically, you can deal with weight sharing with this algorithm. So with like a convolutional neural network where many weights are constrained to be the same. However, this algorithm will not assume that they are the same. And so it will do a lot of additional work that it would not need to do. So like work out every weight separately as if there were no weight sharing. So it's vastly more work than is necessary. So we're working on that. It also doesn't work for pooling layers, which are very common in continets. So yes, this is not at the stage, fortunately, of being able to go and hack somebody's neural network. If it were, then we wouldn't be telling you about it necessarily. Or at least,
thank you.
Yeah, well, like, yeah.
All right, so perhaps we can stop the official talk time here and